Good morning still to everybody. Thank you all for coming. This is a really interesting room. It's nice and cool in here. I was in the main room before. It was incredibly warm, so very happy to be in here. This talk is about reactive programming, reactive architectures. I'm Rob Harrop. Sorry if you went to my previous talk to hear all this again. Used to, in a past life, I was the co-founder of SpringSource, Spring contributor, writer, speaker. This is the first year in many, many years I've actually done any public speaking. So it's nice to be back. These days, I am CTO at Skipjack, which is a company doing machine learning to drive performance optimization and performance management. We have an office here in Krakow, so I come here quite frequently. Very nice to be finally doing a session here. And Reactive's something that I'm kind of becoming increasingly interested in because it fits quite well with our domain. And the more and more I talk to people about it, the more I realize there's kind of a lot of, I'm not going to say misinformation, but there's not a lot of clarity about why Reactive is useful, what it means to people. There are lots of great talks about the details of Project Reactor or the details of Reactive Java or whatnot. What I want to do in this talk, though, is I'm going to show some details, I'm going to show some code, but what I really want to drive home is the motivation, why you should care. I'm on Twitter, GitHub, blog, whatnot. It's a very simple agenda. We're going to talk about principles and practice. We're going to think a lot about reactive architectures and principles and ideas. Then we're going to see that put into practice. I've got a very, very simple set of demos about Project Reactor. Then I'm going to show you a quick code walkthrough, a real project that we built using Reactor. Kind of get a sense for how you can change your thinking and change the way you code if you're using Reactive. The most important question to ask yourself is, why should I care? Why should I change what I'm doing right now and do something new? Mostly what people are doing now is working. None of us, I don't think, are really struggling with our Java or Spring or whatever we're doing right now. It's not terrible. So we need to think, is Reactive that much better? Does it buy me an awful lot? And many of the kind of motivation talks I hear from other people, or many of the reasons people give, I think are somewhat false. So often you'll hear, well, Reactive is great because it's asynchronous. It's all asynchronous. Well, it isn't the only asynchronous model. Java itself isn't synchronous until you magically add Reactive and all of a sudden it becomes asynchronous. You can do a lot of programming asynchronously with just normal Java. You don't have to have Reactive. Then I hear, well, Reactive is fast. It's great for performance. And that may well be true. But Java itself is also fast. Many people have built fast systems in Java before Reactive. So maybe that's a bit of a myth as well. Maybe that's a bit of the wrong road to go down. Then I hear, well, Reactive is super stable. It has back pressure. But again, people have been building systems like this with back pressure and stable, reliable systems before we had Reactive. And it took me a little while to figure out why Reactive really caught my attention, because it was none of those reasons. We can write performant, asynchronous, stable Java code without Reactive. What caught my attention was this idea that architecture is fractal. And this is something that I've been throwing around in my mind for probably 2 years now, maybe even longer. The idea that you can use roughly the same abstractions at many different layers in your systems thinking, and it can carry through and it can be useful. And a lot of this, in my mind, stems from studies. So back in the UK, I did some studies. One of the things I studied was CSP, Communicating Sequential Processes, which was created well before, I guess, nearly everyone in this room was born, by Tony Hoare, a famous English computer scientist. And it's a very elegant, simple model for thinking about how a system is composed of processes that are sequential, but then communicate by message passing. And it's this incredibly powerful abstraction. You can use CSP to describe very low-level interactions between maybe two objects in your Java code, all the way up to describing how several microservices communicate, and then even beyond that, thinking about how two completely different systems that are composed of microservices, that are composed of objects, how they communicate as well. So you kind of get this fractal nature. Very recently, well, actually not so recently anymore, maybe about 4 or 5 months ago, there was a small Twitter storm about an article that got published called Dry is considered harmful. And dry is the do not repeat yourself principle. And I'm sure we're all familiar with that. It's the idea that there should be nowhere in your code that you've got the same code twice. You should always abstract that into a method or a class or whatever. And this article was making the counterpoint, saying actually, in many cases, the cost of duplicated code is a lot lower than the cost of the wrong abstraction. And I kind of buy that argument. I get that. I can see why that might be the case. But it creates this false binary that there's a good abstraction or a bad abstraction, when in actual fact, there's this whole spectrum of how good an abstraction really is. And I have this feeling kind of in my gut that there are some abstractions that are suitably elegant and suitably composable, that they pretty much will work anywhere. And this is why I like reactive, because I think reactive is one of those abstractions. I think it enables us to capture the fractal nature of systems, of objects, of services, of subsystems, and try to describe how our components communicate in roughly the same way throughout. So we can think about reactive systems. We can think about how two different systems communicate with each other via reactive principles. And I don't want to get too deep into what those principles are right now, but let's have a quick jump ahead. Reactive is the idea that you can model things as publishers of data and consumers of data. So it's really streams and consumers of streams. So here's a simple kind of system that I have built, and we're going to see the code for this later on. At the top there, we've got some systems. Does this work? Yeah, we've got some systems which are actually JVMs, and they're publishing data to this system, the hotspot monitor, which is a subscriber to that data. But it's also a publisher of data down to these systems down here, which are, sorry, this is mislabeled. These are subscribers. So InfluxDB or Elasticsearch and Graphite, they're subscribers. So we're thinking about tying our systems together in reactive ways as streams of data and consumers of streams of data. But if we then jump inside the hotspot monitor piece, so we go back and this bit here, we can jump inside that and think about how the subsystems themselves are reactive, how they can be modeled as streams and consumers of streams. So we got the kind of still capturing the idea that the JVM's on the outside here. There's a JVM start API, which is a hotspot internal thing. We have a sampler, which is pulling, like subscribing to data from there and pushing it out to Influx. We have a clock, which is like exposing the clock as a stream. That's an interesting abstraction, and we'll see how that works. This is pushing this out to a repository, which is subscribing to that data. The web stuff is subscribing to that data. And if we have kind of WebSockets or server-side events, then you can think of the browser as a subscriber. So the whole thing is reactive. And the idea is that data flows in here, it flows through the system, it gets combined with other data, and it comes out the end. So it's all this stream of data. But then we can also think about reactive objects as well. Like right down at the class level, we can think about how we can model two interactions as reactive. So here's a simple example of that. I've got like this JVM. There's an object that represents that in the hotspot monitor, and it's got some monitors, maybe for total compiles and on-stack replacement compiles, and it's emitting values, and there's subscription. So this is an object, this is an object, these are actual objects, and these are objects as well. So streams of data between systems, streams of data between subsystems, and streams of data between objects. Here's another example of how I've done this in the hotspot monitor, seeing this time that we've got kind of a host object, so this is the machine that we're monitoring. And actually, as JVMs come and go, one starts, one stops, we need to see that stream of events. So you can kind of think about it like event streaming, But that's too narrow a view in my point. It's not just events. It can be all kinds of data that you want to share between systems or subsystems or objects. And there are some kind of core principles that back this up and why this is useful. And we can look to the Reactive Manifesto, which is somewhat adjacent to the idea of reactive programming, and think about what these ideas are. So the Reactive Manifesto calls out 4 things: resilience, responsiveness, elasticity, and this kind of asynchronicity, message-driven approach. We're not going to talk about elasticity here. I don't think it's as relevant for this, but this is the idea that a real system that's kind of truly reactive will react to increases and decreases in load and will scale up and scale down. Resilience is interesting because we have to keep our systems alive. We want to make sure that as kind of operating conditions change, as the new JVMs come on board in the hotspot monitor, or new monitors arrive, or new sampling data arrives, that no matter what happens, we can kind of keep the system up. And one of the key abstractions for this in reactive is this notion of back pressure. This notion that the subscriber really controls how much data it wants from the publisher. And this is one of the areas where kind of asynchronous, resilient programming becomes easier in reactive than it is perhaps doing it by hand, because they've pulled out this notion of back pressure. So let's consider this. I've got a total compiles monitor, so something that's monitoring the number of JIT compiles in a JVM, and it's publishing some number of those every second maybe, and that's Q. I want to publish these to my InfluxDB time series database, and that number is N. And then the client can obviously do some fixed amount, roughly based on how fast the database can process. It's asking the publisher for data, and the publisher's asking the sampler for data. When N is greater than M, we have back pressure. So the amount available is greater than the amount required. There's back pressure. And we can decide what to do in that scenario. The traditional, normal approach, if you're not using reactive, is to take the very sophisticated approach of burying your head in the sand and ignoring this, and then just having your JVM explode when it runs out of memory. With reactive, though, we're smarter. We can choose to batch that data. We can choose to drop old values, maintain only the latest, try to push back on the upstream. And you can imagine kind of flowing all the way back to the end to say, stop, 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 go again. Stop, 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 go again. And if at any point in time you can't do that, you can decide what to do. And the key thing here is it's better to have slightly degraded service than it is to just completely crash and die. Responsiveness is also a thing that we care about. And my previous talk was about performance, was about latency, and my day job is kind of really focused on this issue. People want to have responsive systems. People want to create good experiences for their customers, whether that be some users who are buying something from a website, or whether you're making a microservice that somebody else is consuming. You don't want to give a bad service. So responsiveness matters. And one of the key ways of handling this in Java and in Reactive is to use asynchronous processing. And I had dinner with Alex Sejovic last night, who you may have been to his Birds of a Feather session last night. He's doing another Reactive session after this, which I highly recommend. And we had this long conversation about whether or not it was too hard to do asynchronous processing in Java without Reactive. And it's hard, but it's not too hard. But Reactive does make it easier, because all you're thinking about is publishers of data and consumers of data. And the reactive infrastructure handles this bit here. It handles whether it's asynchronous, whether it's synchronous, where it goes on a queue, what thread does what. That's all just a kind of a wiring decision, if you will. You don't have to program that. So it's message-driven as well. If you think about this, the fundamental abstraction is message-driven. I publish things to you, you consume them. It's a bit like JMS, it's a bit like RabbitMQ, it's a bit like Redis messaging. It is a kind of publish and subscribe model, because you have a publisher and a subscriber. And that leads us quite nicely to this discussion of reactive streams. So the genesis of reactive programming is quite complicated. But in Java, there's a project called RxJava, which has the two kind of main classes are the observer and the observable. And then there's Project Reactor from the guys at Pivotal. and they have the flux and the mono, which no one knows why they're called that. It's completely nonsensical, which it probably doesn't make any sense to anybody here, but flux and mono are the name of two diseases in England, so it's kind of a strange name for reactive. But in an aim to try and capture the core essence of this, because there's also akka on the Scala side, they all got together and they kind of created this reactive streams abstraction. There's this idea that no matter what implementation you're using, the core architectural and conceptual principles are the same. So in reactive streams, we have a publisher of T, so it publishes some type, and basically all it does is have a subscribe method, which is the subscriber gets passed in, and then it starts publishing things to that subscriber. One thing to notice is that all of these methods return void. That's because they're asynchronous. There's no return value. So you're not getting a publisher and then saying next, 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 next. It's not an iterator like it is like a Java iterator. You're passing it the thing to call back to, which is the subscriber, and then at its leisure, it's going to call back to you. And this is the subscriber, which is also a subscriber of T, so some value T. There are lots of interesting callbacks here, and this is one of the nice things about reactive. It captures all of the things that can really happen when you're consuming asynchronously. It doesn't just assume that you're going to have the happy path of everything works all the time. So obviously you need to be able to consume the data, which is the on next. So every time you get a new thing from the publisher, your subscriber gets called on next. And it's usually quite handy to kind of know when you're starting, like when your first when your first message is about to arrive. And you can hold this subscription to do interesting things, and we'll see that next. But these two are very handy, on error and on complete. So when it finishes nicely, it's kind of stopped, there's no more data in the stream maybe, I get an on complete. But if something goes wrong, I get an on error. And many asynchronous models, many kind of handcrafted asynchronous models, will ignore this and probably this as well. But you can't ignore that because it's asynchronous. Things are happening separate to you. You might get interrupted. You might run out of memory. You may even be pushing down the long stream towards going to a different machine. So it's very important to capture failure, completion, start as real events that you deal with. So we talked before a little bit about back pressure, and one of the very interesting and probably most confusing things when you first start using reactive is if you subscribe and you pass in your subscriber and then you sit there waiting for data, you will get nothing by default. And that's because you basically implicitly have full back pressure. You're not actually requesting anything. You have to request data by calling request on your subscription model. You're saying, please give me some data, please give me some data, please give me some data. And you can do that at your leisure. So it's easy for you as a subscriber to control how much data you want. Maybe you're limiting that based on some downstream pressure from an HTTP client or something. Or maybe you just want to limit your memory profile. All these things are available to you. And you can also cancel. There's no inherent thing in the model that says you have to subscribe to every piece of data that's available to you. In my hotspot monitoring tool, maybe I want to subscribe for 20 minutes and get some data about the compiler, but after that I want to disconnect. So I can cancel my subscription. I don't want to be there anymore. And this very innocuous looking interface, the processor, kind of looks pointless at first. It's like, why would I care that something's both a subscriber and a processor? And I will admit to not quite getting it myself at first. Like, what's the point? Why do I care? And I wrote most of these slides on a flight to San Francisco last week, which is the most productive time I've had in about 6 months because I couldn't get any internet access. Although Virgin are now conspiring against me by offering to sell me 11 hours of Wi-Fi access for £15. But I resisted. This interface is how you compose operations on reactive streams. And this is where the true power of reactive comes. It's not in building something that publishes data and building something that consumes data. It's in being able to add additional operations in between those two things. And if you think about it, an operation that sits in between a publisher and a subscriber must be a subscriber to that publisher and a publisher to that subscriber. And that's where being a processor sits. It's this set of operations you can apply to streams. And we're going to see that and see how powerful that is. It's a phenomenally powerful abstraction. So I could have chosen many reactive streams implementations, and I will be very clear to say I can't recommend one over the other. A bunch of my friends work at Pivotal, so I use their implementation, despite the stupid naming conditions. They have two implementations of the publisher. They have the mono and the flux. The mono is something that will return 0 or 1 element and then complete. The flux is something that will return 0 or many elements and then complete. Not totally convinced by the arguments that those two things are necessary, but they're making good use of that in the new work they're doing to make Spring asynchronous. So kind of give you a very quick preview of what's happening here. If you're doing Spring MVC work at the moment, and you're writing applications in Spring, where right now you're probably consuming JSON or something similar as an object, and you're returning an object to be translated into JSON, in Spring 5, you'll be able to consume mono and flux and return mono and flux of those object types, and then take advantage of kind of complete streaming of data in the web tier. And when you think about plugging that into HTTP2 or WebSockets or server-side events, your code hardly changes, but you're able to deliver and consume asynchronous data without having to see that. It's very powerful. So I've just jumped ahead. What I want to do now is very briefly kind of talk you through the project Reactor API, and then we'll do a deeper dive into the hotspot monitor. This is the worst position ever. Okay. So I'm going to open my very well-titled reactive intro. And we're going to start with this. So the simplest way to create a flux, a publisher or something, is just from some raw elements. So flux has this just method where I can kind of create. I can certainly turn on the presentation mode, yes. Let's do one or the other. Let me increase the font. That didn't actually do what I expected it to do. Let's go for... Let's go a little bit bigger than that, actually. You see that okay? Cool. I was saying in my previous talk, I've just switched computer, so 24 font size on this computer isn't as big on my previous computer, so still getting used to it. So we can start by creating some simple fluxes from some raw data. So now I have a flux that's going to emit those three items in order, and I want to do something with them. So I can subscribe to that. And there are a whole bunch of options for the subscribe method. You can plug in a full subscriber implementation, but actually you can just pass in a lambda that will take the items. And what happens here is, behind the scenes, there's just infinite request value, so I can just send me everything you've got, and I'll deal with it. And I want to print this out as hello plus the name. And then we can run this. He says. And there we go. So we're basically just streaming over that. Very, very simple. We can add more items to that if we want to. Let's do that. So let's now add in, and then we can do that. So it's really, really simple. But, like, why? I mean, it's just as easy to do a list, and we can do a stream in Java 8. So this isn't where the power comes from. The power comes from when you start to do more kind of asynchronously interesting things. So let's consider what we can do if we were to add like an asynchronous stream into the background. So what I'm interested in here is trying to figure out, oh, I've already got it. So here I want to create a flux that emits something every 50 milliseconds. So this is the interval operator. It will create 0, 50 milliseconds later 1, 50 milliseconds later 2, blah, 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 blah. And then I'm going to comment this out. Then it's going to print the thread's current name, and then it's going to print the thread's current name. So let's just run this and see what happens. Oh, interesting. So it's kind of printing out the names. Let's just tweak that slightly and add another, let's add an interesting subscriber here. So you can see it's kind of interleaving these things. And there's a couple of interesting things going on here that I want to point out. So first of all, I have a flux that's actually doing something active. So it's kind of created a thread in the background. So it's asynchronously emitting this interval counter. I'm able to peek into the stream. Did you notice that originally I didn't actually supply anything to subscribe? So this do on next is a very interesting way of peeking into the stream. And when we look at hotspot monitor later on, we'll see some really interesting use cases for how we can create some operable systems by using that peeking. Then at the end in the subscribe, I just passed in the consumer. I'm using Java 8 method references here, so this is just a consumer that takes a value and prints it out. What's interesting here is if I want to change how the publish and the subscribe happen, like maybe I want to move threads, I can add this in here. So I'm going to imagine this is a chain of publishers, because remember we talked about the processor. This is a processor, this is a processor, this is a processor, this is a processor. So in here, I'm going to now switch what thread the publish happens on. So publish up here is happening on one thread, but publish from here onwards is going to happen on a different thread. I'm able to completely change in my chain of operators where publish and subscribe happen. So let's kind of quickly see that. So we see in the console at the bottom here, the initial call to do on next is going on the timer thread, but then the second call, the second peak, is actually happening on the scheduler thread. And you can create any kind of weird and wonderful wiring that you want there. So this is interesting, but what's most interesting is trying to figure out operations that allow us to transform the data. So let's take a quick look at that. And this is just a preview of the real demo. I just want to give you some idea of the main constructs. So I want to create a flux that's just going to publish the first names this time. I'm sure you're all familiar with Dr. Dave Sire, famous. I realize I've missed an equals there. Oops, can't spell my own name. It's been so long since I've done a live demo. It's actually, I used to be very good at this, and now it's just incredibly frightening. So we've got two fluxes now, and I'm interested in combining them to try and get my names back. So what we can do is we can say fn zip with sn. So this is going to zip them together. And what do we get out at the back of there? We get a subscriber. And what does that look like? Let's have a see. Let's print it out. Print ln. So automatically, we've got them with this kind of comma in there, and I wonder why that is. Actually, what's happening behind the scenes here is the reactive infrastructure is creating a tuple for us, so it's taking one stream and creating an object with the two things in it. So it's a bit interesting. So we can actually map that now if we want to change that somehow. So I'm going to put dot. So if you've been using Java 8 streams, you'll be familiar with how this works. You can kind of map or transform these streams. So what I have is a tuple, and I want to map it now into a string with my actual name in it and with Josh's actual name in it. So let's do that. I want to put T1. Oh, this is the very frustrating, cannot capture these things. So let's do it here. So now I've managed to actually combine it into a string. And this weird lambda-looking thing here is a bifunctor, so it's just a function that takes two arguments. And I want to transform this now into uppercase, because I want to shout at you all. So I'm going to use the map operator here, and we're going to do string to upper. I'm going to run that. Oh, it doesn't work. Non-static, oh, of course. That's frustrating. So we'll do this instead. For some frustrating reason, my IDE has stopped working. That's a dirty cheat, but it'll fine. And there we go. So we're able to transform that stream with a map. And very, very quickly before we dive into the main demo, let's take a quick look at the full set of operators on Flux. We can buffer things. So imagine we've got a stream of names. We want to catch them into a stream of lists of names, maybe every second or every 100, we can do that. We can cache these things, so we kind of like, you can replay them. You can collect groups of functions or groups of fluxes together and map them into one, which is very, very funky. There's tons of these things. If I spent time going through every single one of these, we'd be here for like 2 or 3 hours. What I want to do instead is show you, in a real context, what these things look like. So before I do that, I want to just very, very clear. Reactive Streams is the model. It's kind of the interfaces. So you're thinking in terms of streams. You're thinking in terms of reactive streams. Project Reactor is just one implementation. There's also Akka. There's also Rx Java. And if we're using Reactor, we have Flux for 0 to many, and we have Mono for 1 to many, for 0 or 1. And it's the Reactor itself that manages the back pressure, and it's Reactor itself that manages the asynchronous processing. So let's actually see this in real action. I'm going to start with the simplest piece of this tool. And what this tool is doing is, every time a JVM starts, it allows us to attach to it and get some internal state. So when hotspot JVMs are running, they expose a whole bunch of interesting internal state. The reason why I did this is we're very interested in tracking how the JIT compiler is working. You can't get JIT statistics via JMX. You have to get them from the internal state. So we're using this to get into that. And the first interesting thing is this. It's this kind of tick subscriber. So I create a flux interval, which we saw before. It's going to emit 0, 1, 2, 3, 4, 5 every tick. And I want to drop these things on back pressure. You can imagine if this is a very small period here, it could flood the downstream system. So I'm happy to ignore ticks. I don't need them all. And then what I'm going to do is rather than just emit 0, 1, 2, 3, 4, what I actually want to do is emit the real time. And this is a testing hack here. In testing, it's very hard to test against something like current time millis that moves. So you can pass in any supplier of long, which you can hard code in the test. So if we can see that, actually. And this is interesting, right? So now I'm testing these things. How do I do that? Well, I've created a publishers.tick. I'm always going to return a dummy value for the time, so I'm not trying to test it against system current time millis. And Reactive provides this test subscriber. This is incredibly powerful. So I can subscribe to my Flux on my publisher, and then I can do a whole bunch of interesting assertions. And one of the things I can do is say, please await however many values I supply and verify each one matches. So here I'm validating that each value of the next 3 is equal to dummy. And we can run this test and see if it passes. And obviously, that's really, really simple. What if I want to check, though, that it does actually call system current time millis? What if I want to check if that bit's really working? So here, instead of passing in a dummy time sampler, I let the tick use the real current time millis. And instead of passing in a value to assert with, I actually pass in an assertion. And all the assertion is going to do here is just say, did the value I get, is it less than the real current time? Which obviously should be true as well, unless we've gone back in time. And we can run that as well. So now I have a flux that is the clock for my system. It models a constant stream every period, maybe 50 milliseconds or 1 second or whatever, and it will emit the current time. And if you think about what we're trying to build a sampler where every so often, every second or whatever, we're going to sample some value. This serves as the sample heartbeat. It's however often I want to sample something. Really useful. What we're sampling is JVMs. So what I'm interested in doing is finding out when JVMs arrive and then trying to get access to their state. So I want to create this thing called a VM watcher. And what I want to see is a stream, a publisher, a flux of VMs every time a new one starts. And where this is interesting and why you want to see this code is this shows you how to bridge from an external event publishing system, so something that in the background already has a listener infrastructure. Maybe it's Java AWT, mouse clicks, or in this case, it's JVM start host events. You want to bridge that external event context into a reactive context. So let's see how that works. This is one of the nicest APIs they have, and I'm quite pleased with the new developments they've done. So that's the wrong class. That's why it doesn't make any sense to me. So here's the watch host method, and we're going to call flux.create. And this gives us access to this emitter, and it's the emitter that we can call every time we see a new event from the external context. JVMstat has this awful API. It's like many, many unchecked operations and so forth. So it's very nasty to work with. Here I'm cleaning it up. And all I'm doing is saying that every time I get a VM status changed event from JVMstat, please emit those events out to the flux. And this basically here shows you how that works. We're going to stream and for each over the events we get from JVMstat, and for each one, signal an event onto the emitter. And if I'm a subscriber now, I'm seeing those events. I'm seeing every JVM that arrives. And I'm able to then kind of hide all this messy JVMstat code behind my reactive abstraction. There's a few more interesting things that you need to do here. If you remember back to the presentation earlier on, I said one of the key things you need to be able to do is cancel your subscription. You want to be able to stop listening to data. And if this wasn't done well, there's a potential memory leak. Imagine what happens. We just stop listening, but we don't clean up the listener we created to JVMstat. Well, if you keep subscribing and keep stopping and keep subscribing and keep stopping, those listeners stay around. And eventually, you just run out of memory. So you can tell the emitter what to do when any subscriber does a cancel. And here I'm just basically saying, right, okay, set the cancellation to be this lambda, and in that lambda, please just remove the host listener. So I'm able to clean up after myself. And now I've got a fully encapsulated external event publisher, external system behind this reactive interface. And if you go back to the actual interface description, all I need to do now is subscribe to the VM. Likewise, once I've got these VMs, I'm kind of interested in figuring out how I can sample some data about them. I want to be able to figure out just how many on-stack compiles is the JIT doing. And to do that, I need to be able to sample things. So I have this sample metric method here. What metric am I sampling? What interval? What unit? And it's going to return a flux of a tuple with a long, which is the time, and a number, which is the sample value. And this is tuple2 class is something that comes with Reactive. So we see how this works. We're going to see kind of pairing a whole bunch of interesting fluxes together. Ignore most of this code. So here in sample metric, I'm going to find the JVM stat monitor. Every JVM stat method throws a checked exception that you can do nothing about. So that's what these do or throw things are for. And then here's the really interesting piece. So I'm using my previously defined publisher.tick. So I'm going to create my clock at the interval I want, at my sample interval. I'm going to map that to a tuple where the first part of the tuple is the time, and the second part is the value of the monitor. So now I've got a tuple that is basically emitting a steady stream of samples. If I don't limit that, it will basically keep going forever. And there's a very interesting side effect with JVM stat, which is after the JVM goes, you can carry on sampling. You can kill the JVM, and you can carry on sampling all the way until you restart the machine. And the reason for that is that the samples are communicated between processes using a memory mapped file, and that file just kind of basically stays around as long as you've got it open, so you can keep sampling the last value again and again and again and again. So what I really want to do is limit this stream and stop it the moment the VM terminates. So we have this take until operator, and you can basically pass in a predicate, so a lambda predicate, or here I've passed in a mono. And it will now, that stream will take values until this mono emits its one value. And this is, again, working around a really messy part of the JVM stat API, which is termination events for VMs are incredibly unpredictable, especially on the local machine. If you're monitoring a VM that's remote, because the network connection disappears, you get a termination event. If you're monitoring a VM on the local machine, you basically never get an event. So the only way to do it is to keep polling and say, do you still know about this VM? Do you still know about this VM? And then eventually, when it says no, you can emit your termination event. So here I have a mono, and every second, it's checking to see whether or not that VM is still active. And the moment it isn't, it will emit the VM's PID. And that's the mono complete, that's the mono done. I'm able to use this in my web UI to track when VMs come and go, but I'm also able to use this to limit the sample stream so that that sample doesn't stay around forever and ever and ever. And I alluded earlier how you can start to think about reactive architecture as being fractal, and this is a perfect example of that. I'm composing two objects together to make one stream, and then I'm composing more objects together to make one stream, and then I'm going to make some subsystems. So I've got the publisher subsystem, I've got the sampler subsystem, and then likewise I'm pushing out to other systems using reactive principles. I'm going to open source all this code as well, so anyone who's interested, I'm going to put it out sometime next week. You'll be able to see it on my Twitter. So now we've got the ability to sample a JVM. We've got the ability to see when JVMs come in. What's missing? Well, I don't want to sample absolutely every single value that they have. At my last count, there was about 250 counters in the internal data. I'm only interested in a handful. So we have this idea of a statement of interest. So I can express that I'm interested in seeing the sun.ci.standard compiles counter, and I want to see it every 1,000 milliseconds. And the way that we do this is that when you start a JVM you want to monitor, you put a special system property there, and then when we see the JVM come in, the hotspot monitor passes those system properties and says, we want to monitor this one. We're going to monitor these counters. And we want to see that stream of statements of interest as a flux as well. And this one is it's quite complicated, but it shows something interesting that I want to highlight. So we have a stream, so a Java stream, not a flux, a Java 8 stream, and I'm going to filter over it and basically just clean up all the system properties. It's kind of irrelevant what happens here. But what's interesting is I've used the peak, the do on next, to put my logging code in there. So imagine you've got all these streams and all these complex transformations going on. It can be quite hard to see what is going on. But if you want to pull apart the individual steps, you want to see how maybe each map takes effect, or you want to see how each zip and concat takes effect, then using this trick of doing do on next with your logger in there is really handy. It's a really, really nice way of figuring out, I can see that this has happened. I can see this is running. I've found this to be quite useful. When I first built this, I took a different approach. So remember, this is a publish and subscribe concept, so I can have multiple subscribers. So what I first created was the main statement of interest subscriber and a specific subscriber for logging. And the problem with that, obviously, is that logging that you've seen the statement of interest doesn't necessarily mean that the main code has seen that, because they're not linked together. So doing it in line here with the peak is a much better insight into the consumers that you're seeing. It's much better to do it this way. You don't get as many false positives. So now I can see JVMs come on board. I'm hidden from JVM stat. I can monitor those JVMs. I'm hidden from JVM stat. I can see what the statements of interest are, and we can expand where those come from over time. I want to piece this all together now into a sampler, and this is where the real power of Reactive is shown. This is fairly mind-bending at first. Just looking at this, it looks very simple, but it took me a little while to write this code. All I'm going to do here is use flatmap. And flatmap will basically take a flux and map over it and basically combine multiple fluxes into a stream in a nice way. So I'm watching the local host, getting the PID, matching it to the PID of the SOI, so I'm basically merging two fluxes together into a long stream and then turning it into samples. And I'm doing another flat map here. So if you imagine the statement of interest publisher emits a finite number of statements of interest, the VM is finite, but the sample is effectively infinite. And here we're able to take that and kind of weave it all together into this complex chain with very little code. I tried writing this by hand at first, and it was incredibly painful. I think I ended up having like 85 lines of code, and it didn't work perfectly every time, and I must have spent hours on it. So this ability to sort of take individual fluxes and merge them into streams of fluxes is very, very handy. And now what we have is just a steady stream of, for every VM that I'm looking at, for every statement of interest I have, samples coming out. It's all the samples for all the VMs, for all the statements of interest in one stream. And what I want to do with that is consume that and publish that to my InfluxDB. So the final piece in the puzzle is having something to publish. I'm using Influx, and here we can see some really interesting things. So I'm using the sampler. I'm mapping each sample into a point, which is a domain concept from Influx. I'm buffering those up into batch sizes of either 100 or roughly like 1 or 2 seconds. Then I'm going to turn that into a batch object, which is another InfluxDB concept. I'm doing on back pressure drop. So if my downstream influx is very slow, I'm happy to start just dropping samples. Doesn't matter if I lose a few samples. But I'm using a logger to warn that I'm dropping those things, so you can kind of get some insight. I've got this trace here to say that I'm publishing these batches. And then I'm basically using a separate thread to do the publish, so I can isolate the publication and have the back pressure propagate. One thing here, and this is very important. Back pressure only really works if you're using different thread pools across the subscriber and publish boundaries. If you're all on the same thread, everything's happened synchronously, so it's happening basically as fast as you possibly can. And rather than just passing in a simple consumer, I pass in a full subscriber. So in my onSubscribe callback, I request my first batch. Then in my onNext, I write them to influx, and I request the next batch. So rather than using the default infinite stream of data, please, I want one at a time. And this will mean if the influx gets overwhelmed and stuff starts backing up, it will eventually get dropped. It's very cool. Another handy little thing I did here was this do on complete. Testing these asynchronous things can be quite hard. And I needed to know in my test when this had finished. So I put this do on complete to call this protected method. Then in my tests, I override that protected method and wait for it, basically. And I can then make sure my tests don't exit until the publisher has really finished. It's a very handy little trick that I have taken great advantage of. And the end result is this, is that I have all of the internal metrics from my JVMs going into influx and being mapped into Grafana. But because I've taken the time to abstract JVM stat behind Reactive, and I've basically captured most of my concept in Reactive, it's very easy for me to compose this in many different ways. In particular, one of the things I'm now doing is adding the ability via the browser to add new statements of interest. And all I need to do is create another flux that emits those statements and merge it with the existing one. Nothing else has to change. So the amount of isolation you get using Reactive is incredible. So to quickly summarize, don't get het up or don't get trapped in this mindset of thinking that Reactive is all about asynchronicity and performance. More importantly, it's about design. More importantly, it's about architecture. It's this very powerful model. As you saw, just a small snippet of the operations you can perform on those streams, the compositional power is incredible. So you can think about Reactive as just a day-to-day model, even if you don't have particularly high performance requirements or particularly high asynchronous requirements. Publishers are capturing output from systems, whether that's your own systems or external systems or pretty much anything. And subscribers are the consumers. Back pressure is controlled via your subscription, and explicit back pressure is a really good way of managing memory usage and processor usage and just general utilization. Reactive Streams is the interchange interfaces, if you will. You may have noticed that in my implementation, I didn't make great usage of the interfaces. The reason for that is the operators that we saw, like interval and map and so forth, are not defined in the standard. They're only defined in the implementations. So as yet, I still think the Reactive Streams kind of commons effort is relatively undefined, but conceptually, it's a really good model. Project Reactor is very sophisticated. We saw like hardly any of it. It has a whole I/O module to handle reactive TCP and HTTP and all of these kind of complex things. It's a very well done project. It's enjoying a lot of active development at Pivotal. It's well supported, so I highly recommend you all try it out. And that's it. Time for questions, if there's any questions. I really can't see anybody. Oh, there's one here. Okay, great question. I think your question was, back pressure aside, the Reactive Streams is very similar to the Java 8 Streams API. Why create a different Stream API? Okay, so they are very similar, except for a subtle point that I probably was a bit too quick in going over. The Streams API has no real way to find out when things go wrong or when things complete. So all you really get is the next. And They did consider trying to use the standard kind of consumer and producer interfaces that are in Java 8, but because there's no callback to say you're done, or there's no callback to say it's all gone wrong, it wouldn't work that way. So that's the reason why there's a specific interface for that. You're welcome. Any other questions? In which case, thank you very much, and go and enjoy your lunch.